Okay guys, so check it out. This is a sneak peek of what we're doing today. We've got our graphics card here running with CUDA, and it is processing tons and tons of calculations for our convolutional neural network that we are going to build. And we finish here. You can see this round finished at 72% accuracy. And we have a graph for our accuracy here showing our training and our testing validation accuracy, and we also have our loss graph, which is going to give us more information. But overall, this is going to be our first look at the CIFAR-10 dataset. This is part 2. In the first episode, I introduced the CIFAR-10 dataset to you, which has all kinds of images in it, has 60,000 images, and today we're going to build a convolutional neural network to classify those. In this episode, we continue our look at the CIFAR-10 research dataset, and we're going to go ahead and build a convolutional neural network that's going to do some classification so that we can predict what pictures are when we run it through our model. If you have not watched it yet, make sure to check out part 1, where I introduced the CIFAR-10 dataset. Okay guys, so this is a fun one today. You remember these wonderful pictures, these wonderful high resolution pictures that are part of the CIFAR-10 dataset. They're actually used specifically for this purpose to allow us to create our models and test how well we can make computer vision work. Now I will draw your attention to the task manager here, and you'll see I have this CUDA selection available, and that's because I installed CUDA from NVIDIA. Now if you have a NVIDIA card, you may be able to use that for data science projects. So check it out. Now this is what we did last time. In our last video, we got our libraries ready. We prepared some data from the CIFAR-10 dataset, and we printed out some PNGs and just on screen here so that we could see what the data looks like. This big dataset that we download from University of Toronto. And today we're going to get rid of that block that spits out some data because we sort of know what it looks like already, and we're going to get to work on building our model. Now the first thing I'm going to do is I'm going to get our validation set ready. This is a validation set that works inside of the training set, so it'll be taken from the training data set. So we had 60,000 images in the CIFAR-10 dataset, and we've already taken 10,000 of those for our testing, and we are going to take another 10,000 for validation, and that sort of works as part of the training. It helps to see what's happening there. And so you can do that. So that is 10,000 for validation from X-train and Y-train. And by doing that, we're also going to reduce the actual training set by 10,000 as well. And so there will be actually 40,000 used for training, 10,000 for validation, and then 10,000 for ultimately for testing at the very end of the process. And so that'll create our X underscore val and Y underscore val variables, and it'll reload the X train and Y train with the remainder of the images. Now I'm going to put our model as a return value from a function. You don't have to do this. I like to do it. In today's example, we're just building it straight out with no arguments. However, I do have a version of the of my model function that allows you to have all kinds of inputs and things like that, and it'll build the model for you, which I can maybe show you in an upcoming episode if you're interested in that. But for today, our model will be very simple. The function, we'll just say that our model is sequential, and then we're going to add the two layers, the CONV2D and our max pooling. We're going to use those two in our model today. We're going to stack those, and we'll just see if we can get any kind of results out of our model today. Now, Conv2D is a convolutional layer that is in 2D that is very good in helping with images, and max pooling can reduce the computational cost as well as help with overfitting and things like that. And it uses strides, which basically pass over an image to help with those things. And so max pooling is one of those things, one of the many sort of things that you can use to try to improve your model. You can use it or not use it. You can actually just stack Conv2D layers on top of each other, and they will start to build that network. And so you can see here in my first layer, I have 32 filters. The kernel size is 3 by 3. The input shape is 32 by 32, and we're using the activation RELU, and then we're using max pooling 2D to downsample that, and then we'll do the same thing on the next layer of our network. We're going to do another Conv2D, and I'll do 64 filters this time, and we'll see how that works. Now, these are all parameters that you can customize and tweak, and it will be different for every case. So depending on the kind of data that you have, you may actually end up with very different requirements for parameters, for the number of layers, for the number of filters and kernel size and things like that. Those will all change depending on the kind of data that you have. And so for today, I'm just experimenting. We're going to build this with several layers so that we definitely are in our convolutional neural network. And we're going to have several layers here that we're going to run calculations through. Now I'm going to add dropout, which you can check out. Dropout is also a method for reducing computational complexity. It can reduce the amount of information that's fed forward through your model. So dropout is kind of, it's optional as well, and some people recommend not to use it. It really depends on the situation. And then we'll flatten our output so that we can get our number of classes in the output, which is there. We've got our number of classes. That's going to be the output dimension. And then we're going to add our softmax, which is typical for the last layer of the model. After we've added our last layer, which outputs the number of classes that we know are going to be output by the model, in this case 10, which are the list above: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. We're going to compile the model before we pass it back as a value from the function, and we're going to use a loss function and an optimizer, and we'll specify some other parameters. And we're going to use mean squared error in our first time through here. That's one of the loss functions that you can use when you have several different categories or classes, and it's not binary. And we will also use categorical cross entropy, which is another loss function. And the optimizer atom is a good one for this scenario. And so we'll put our model as the return value for our function, and then we can say model equals CNN underscore model. Now, if we had all kinds of different parameters that we wanted to change, we could do that with a more complex model function. So just be aware of that. In today's example, we're just saying model equals CNN underscore model. And then we'll print the summary of that. We'll print model.summary, and now that's going to give us some output to tell us what our model looks like before everything starts running. And then we can do our fitting of the model, and we'll do that by loading a results variable with information that comes back after the model.fit has been run. And that's very, very handy. We're going to stick that into some graphs later on, and so make sure you stay tuned for those. Now we're going to pass in our xtrain, ytrain variables into our fit, and then our validation data, we're going to put that in as well. That's actually optional, but we're going to put in our validation data that we created. We're going to do 10 epochs and batch size of 50. Now 50 is pretty small, and this is where the training and everything comes in, and the size of your computer and all kinds of stuff. So 50 is actually a bit small for the setup that I've created here, but it very quickly becomes too big, and the difference is hours versus like minutes in terms of processing time. So just be aware of that. If you do not have GPU processing, then we will definitely see that. And once we've fit our model, we're going to take the scores. We're going to say model dot evaluate, and we'll put in our x test and our y test information, and then we'll print that out in our CNN accuracy statement. We'll just do a print CNN accuracy, and then we'll format the output, and then we'll show that on screen. And so that sort of like rounds it out, and allows us to fit our model, and then we can evaluate the output, and we can see how accurate the model is. And then once we have that with a sort of easy to process set of parameters, only 10 epoch and things like that, and once we've determined that we have no errors in our procedure, hopefully we don't have any typos or anything, then we can go back and we can sort of increase some of our parameters to do a bit more heavy processing, maybe take a bit longer time, and things like that. And so there's our accuracy statement, and I think we're good to go here. Now, one thing to note is that you do not want to run this in idle. It's almost always better to run this. You can see it's cdevdnn cfar10.py. It's a lot better to run this in the console, because the console will deliver better output. Now, you might be using Jupyter Notebooks, in which case don't worry about that. Jupyter Notebooks provide a great looking output as well. I like to be with the simplest of tools. And there you go, it is running, and there's our model information, so you can see that it's sort of identified the layers, and you can see it sort of started running. Now this is with a batch size of 50, and you can see that it starts sort of churning away through the epoch, we specified only 10, and you can see in the top right here that CUDA has started to use the graphics card. And as I mentioned before, processing images and training on images actually takes quite a bit of time. And if I was only using CPU, which a lot of you might have, and I have done this before where I've processed only on CPU, it takes hours. It can take a very, very long time. However, if you have a graphics card that's capable of running this stuff, make sure you check out how to install CUDA and CUDNN, and also get the right TensorFlow version. And you can see that CUDA is just spinning away now. Now this is not as fast as it goes. As I mentioned, we're only processing batches of 50, which slows it down a little bit. But you can see that we're already on epoch 10 of 10, and it looks like we're getting like 65% accuracy or something like that. Yeah, you can see in the last step there, and actually it never got to our output statement because I screwed something up. Yes, I made an error. It says X text is not defined. Did I mean X test? And that's quite a smart message, error message they've got coming out there. I got to fix that TEST there, and that's actually very smart. So that's okay. We know that this was about 60, maybe 67% accurate with 50 epoch. Now, the more you train it, the more epoch you do, the better it can get. But the problem is it's possible to go too far, and that's where you train it so far that it gets to know the training data set incredibly well, but it actually doesn't, test very well in the real world. So there's a bit of a fine line there, and it's a balancing act. It's a bit of an art form, and a lot of trial and error. So if you're good at troubleshooting systems, that might be for you. So I'm going to go ahead and run it again here in the console. All I did just there was I increased the batch size to 150 from 50, and running this on images, you'll see how much faster it is now. Now check that out. It's actually just churning away. It's actually going through those much more quickly than before, and that's because it's processing more at the same time. You can see up here in the top right, CUDA is just hammering along, as well as the CPU. And for this computer, this is about as good as it gets in terms of the computing. I imagine you could push it further and get a little bit more out of it, but those of you with high-end graphics cards, those NVIDIA 3090s and 40 whatevers, definitely you're going to be a lot faster. And even if you have multiple cards, that can also help. So this is already done, and it looks like this one got about 60% accuracy, which isn't really that great. So we ran that through 50 epoch, but we were getting pretty good learning from it, and that's usually a sign that you can still run more epoch to make it learn more, basically, so you can get better results without overfitting your model. And so we're gonna increase the epoch next time from 10. And we'll do something like, we'll blast it up over 100, and we'll see how that goes. But before we do that, I'm going to take and I'm going to plot some information that goes into that results variable that you see up above there, which is really great because it's going to show us how the model learned as it progressed through the epochs. And now that we know we've got a model that can run without errors, that's where we got to just now. Now we can go ahead and we can start to add some information coming as output, and we can start running the model a little bit harder. And so what I'm doing here is I'm just building that plot. I'm going to put legend in there for training and test. and then we'll do the same thing for our loss history, so that we can show if there's sort of a crazy loss curve, then you know that something's up. And so what we'll do is we'll plot it the same way that we did with the accuracy. I'm gonna jump back there and fix that PLOT. There we go. We'll do results.history is equal to validation loss in addition to our loss history there, and then we'll do our legend the same way that we did with the other one, but I will put the legend in the top, the upper left there, and we'll do the same thing. I'm going to copy that and paste it into the other one there for accuracy, and then we'll show that one. So just very quick, we just wanted to add a little bit of code there that's gonna give us a couple of graphs that will give us some insight into how our model's doing, so that we can run this sucker over and over and over again, and each time you can see how it's doing, and you can keep variables or configurations that work and get rid of other ones, and that's what those lines do there. Now let's change our epoch here. Let's do 50, and we've got 150 batch size now, so it's quite a bit bigger than it was before. And let's see what we get if we have 50 epoch instead of 10 like we had before. And as you can see, this is actually blasting through pretty quick compared to last time when we ran it with only 50 batch size. Now if you are running and you put in something crazy like 500 as your batch size and you get all kinds of memory errors, that's when you know you pushed it too far and it's too much for the equipment to work with. That is definitely something that can happen if you put too much through there. Now that being said, if you're running a deep neural network and you're running it on data sets, tables instead of images, now tables can be processed much more quickly, and so you may find if you do have CUDA installed that you can run batch sizes, really big batch sizes like 10,000 and things like that. In fact, your computer won't even kick over to use CUDA from the CPU if your batch size is not high enough. So if you have small batch sizes and you're running deep neural networks on just on your CPU, you'll find it's very slow until you actually create the batch sizes that will utilize CUDA, and then you'll see CUDA start to be utilized in your performance monitor here. And so that's important to note because that will save you a lot of time. I've run it on really big data sets that were just data, tables of information where I was calculating and using a deep neural network, and CUDA operates great on those, and in fact you'll find that it will not utilize CUDA. It'll probably use generally like 25%, whereas it's using 68% when we're doing images. So you can see the difference in difficulty for the computer to work on images as opposed to tabular data. And as you can see, there's our accuracy improving as CUDA does its work there. Our graphics card with the CPU is at 70%, and it's sort of blasting away on those numbers. And as I mentioned before, you could run this in your Jupyter notebook as well. If you're using Jupyter notebooks, and Jupyter has a nice display for this. It looks very similar, except reversed. It'll be on white with black lettering in the output window. And you can also see that the GPU is heating up. This one is at 58 degrees Celsius, and that is warming up. It isn't as hot as it can go, but definitely the CPU or the GPU activity I should say. The GPU is definitely warming up from all of this work. So you might want to take note of that. Make sure you have good ventilation when you're running CUDA and machine learning. You'll definitely need to make sure that your computer does not overheat from all of these calculations and power going through there. And here we go, we're in the last 5 of the epoch of 50, and our results look pretty good. It looks like our training accuracy is getting close to 80%, which is 4 out of 5 correct. However, our validation accuracy is not as high. It's around 72% by the looks of it as we get to the end here. And so it looks like we're going to end up with about 72%, which isn't great, but it's not terrible. I think we could definitely do some work on our configuration. There's our accuracy curve as the epochs were processed, and it is definitely going up, and so is the validation data. So that's looking good, and the curve for loss is kind of what we would expect to see. A little bit of craziness on that validation, but all in all, I think we could definitely proceed with this and do some more configuration and get a lot more accuracy in our model. Looking for the files used in these videos? Make sure to check out my downloads page. The link is in the description.